Space, the final frontier, has captivated human curiosity for centuries. As we gaze up at the night sky, we are reminded of the immense, unfathomable universe that stretches beyond our reach. The stars, planets, and galaxies that glitter above are not just distant objects. They represent the unknown, the undiscovered, and the potential for endless possibilities. Our journey into space is not just a physical exploration, but a philosophical and existential quest to understand our place in the cosmos. In this essay, we will embark on an expansive exploration of space, unraveling the mysteries of the universe, the marvels of space travel, and the profound implications for humanity. The universe, as we know it, began with the Big Bang approximately 13.8 billion years ago. This colossal explosion marked the birth of time, space, and matter, giving rise to everything we see today. In the immediate aftermath of the Big Bang, the universe was a seething mass of energy, rapidly expanding and cooling. Over time, particles coalesced to form atoms, which eventually came together to create stars, galaxies, and planets. The formation of these cosmic structures took billions of years, and they continue to evolve to this day. One of the most remarkable aspects of space is its sheer size. The observable universe stretches for approximately 93 billion light-years in diameter, yet this is only a fraction of the entire universe, which may be infinite in extent. The concept of distance in space is difficult to comprehend. A light-year, the distance light travels in 1 year, is approximately 5.88 trillion miles. To put this in perspective, the nearest star to Earth, Proxima Centauri, is over 4 light-years away, meaning it takes light over 4 years to travel from that star to us. The vastness of space is humbling, reminding us of how small and insignificant our planet is in the grand scheme of things. Within this vast universe, galaxies are the primary building blocks. A galaxy is a collection of stars, gas, dust, and dark matter bound together by gravity. There are an estimated 2 trillion galaxies in the observable universe, each containing millions to billions of stars. Our galaxy, the Milky Way, is a barred spiral galaxy with over 100 billion stars. The Milky Way is part of a larger group of galaxies called the Local Group, which itself is part of an even larger structure known as the Virgo supercluster. These cosmic structures are interconnected in a vast web of galaxies, stretching across the universe. One of the most profound discoveries in recent decades has been the confirmation of dark matter and dark energy, two mysterious components that make up most of the universe. Dark matter, which does not emit, absorb, or reflect light, is thought to account for approximately 27% of the universe's mass. It exerts a gravitational influence on galaxies, helping to hold them together. Dark energy, on the other hand, is an even more enigmatic force that is driving the accelerated expansion of the universe. It is believed to make up about 68% of the universe. Together, dark matter and dark energy constitute around 95% of the total mass energy content of the universe, leaving only 5% as the ordinary matter that we can observe. The study of space has been revolutionized by the advent of space exploration. The space age began in 1957 with the launch of the Soviet satellite Sputnik, the first artificial object to orbit Earth. This milestone sparked a race between the United States and the Soviet Union to explore space, culminating in the Apollo moon landings. On July 20, 1969, Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface, a defining moment in human history. The Apollo missions demonstrated that humanity could reach beyond the confines of Earth and explore other celestial bodies. Since the Apollo era, space exploration has evolved in new and exciting ways. Uncrewed spacecraft have visited every planet in the solar system, and space telescopes like the Hubble Space Telescope have provided us with breathtaking views of distant galaxies, nebulae, and star systems. The International Space Station, ISS, a collaboration between multiple countries, has been continuously inhabited by astronauts since 2000, serving as a laboratory for scientific research in microgravity. The ISS represents a remarkable achievement in international cooperation and the pursuit of knowledge. One of the most exciting developments in space exploration in recent years has been the rise of private space companies. Led by visionaries like Elon Musk and Jeff Bezos, companies such as SpaceX and Blue Origin are pushing the boundaries of what is possible in space travel. SpaceX, in particular, has made significant strides with its reusable rocket technology, reducing the cost of space travel and paving the way for future missions to Mars. Musk's long-term vision is to establish a self-sustaining colony on Mars, ensuring the survival of humanity in case of catastrophic events on Earth. Mars has long been a focal point of space exploration. As the most Earth-like planet in the solar system, it has been the subject of numerous missions aimed at understanding its geology, climate, and potential for hosting life. The discovery of liquid water on Mars in recent years has fueled speculation about the possibility of microbial life on the planet. If life exists or once existed on Mars, it would be a groundbreaking discovery, fundamentally altering our understanding of life in the universe. Mars also represents a potential future home for humanity, with efforts underway to develop the technology needed to establish a human presence on the planet. Beyond Mars, the solar system is filled with other intriguing worlds. Jupiter's moon Europa, for example, is believed to have a subsurface ocean beneath its icy crust, making it a prime candidate for the search for extraterrestrial life. Saturn's moon Titan, with its thick atmosphere and liquid methane lakes, offers a unique environment that scientists are eager to explore. The outer planets Uranus and Neptune, while less studied, also hold many mysteries, with their distant orbits and extreme conditions presenting challenges for exploration. As we look beyond the solar system, the search for exoplanets, planets orbiting stars outside our solar system, has become one of the most exciting fields in astronomy. The Kepler Space Telescope, launched in 2009, has identified thousands of exoplanets, some of which are located in the habitable zone of their parent stars, where conditions may be right for liquid water and potentially life. The discovery of Earth-like exoplanets raises the tantalizing possibility that life may exist elsewhere in the universe. The search for extraterrestrial intelligence, SETI, has also intensified, with efforts to detect signals from advanced civilizations in other star systems. The possibility of life beyond Earth has profound implications for our understanding of the universe and our place within it. If we discover even the simplest forms of life elsewhere in the cosmos, it would suggest that life is a common phenomenon, potentially arising wherever the conditions are right. On the other hand, if we find that life is exceedingly rare, it would underscore the uniqueness and fragility of life on Earth, reinforcing the need to protect our planet and its ecosystems. While the search for life and the exploration of other planets are exciting endeavors, space also presents significant challenges. One of the most daunting obstacles is the vast distances between celestial objects. Even with the most advanced technology, traveling to the nearest star system, Alpha Centauri, would take thousands of years. Developing faster-than-light travel or other advanced propulsion systems is a distant goal, but it remains a tantalizing possibility for future generations. Until then, we are limited to exploring our solar system and observing distant stars and galaxies from afar. In addition to the challenges of distance, space is an incredibly hostile environment. The vacuum of space offers no air to breathe, extreme temperatures, and harmful radiation from the sun and cosmic rays. For long-duration space missions, such as a crewed mission to Mars, protecting astronauts from these hazards is a critical concern. Advances in spacecraft design, radiation shielding, and life support systems will be essential for ensuring the safety of future space travelers. Despite these challenges, the potential rewards of space exploration are immense. Space offers vast resources, including minerals and energy, that could help address some of the challenges facing humanity on Earth. Asteroids, for example, are rich in valuable metals such as platinum, gold, and iron. The concept of asteroid mining, once the stuff of science fiction, is now being seriously considered by private companies and space agencies. The development of space-based solar power, which would harness the sun's energy and transmit it to Earth, could provide a clean and virtually limitless energy source. Moreover, space exploration has the potential to unite humanity in a common purpose. The challenges of space are so great that they require collaboration between nations, scientists, and engineers from around the world. The success of international projects like the ISS demonstrates that when we work together, we can achieve remarkable things. Space exploration also inspires future generations of scientists, engineers, and dreamers, encouraging them to pursue careers in science, technology, engineering, and mathematics (STEM). The philosophical and existential implications of space exploration are also profound. As we explore the universe, we are forced to confront fundamental questions about our existence. Are we alone in the universe, or is life abundant? What is the ultimate fate of the universe, and what role will humanity play in it? These questions go beyond the realm of science and into the domain of philosophy and spirituality. They challenge us to think deeply about our place in the cosmos and our responsibility to future generations. Space exploration has already changed our perspective on Earth. The famous Earthrise photograph, taken by the Apollo 8 crew as they orbited the Moon, shows our planet as a fragile blue and white orb suspended in the blackness of space. This image, along with the iconic pale blue dot photograph taken by the Voyager 1 spacecraft, has become a symbol of the interconnectedness of all life on Earth and the need to protect our planet. As we venture further into space, we are reminded that Earth is our home, and we must care for it as we reach beyond. The more we explore space, the more we realize the singularity of our planet and how vital it is to preserve the fragile ecosystem that sustains us. From the vantage point of space, national boundaries and divisions become meaningless, highlighting our shared existence on this small, blue marble floating in the vastness of space. This realization has given rise to a global environmental consciousness that has only grown stronger since the dawn of the space age. Our exploration of space has also sparked countless debates about humanity's role in the universe. One of the most profound questions revolves around the concept of the Great Filter, a hypothesis in the field of astrobiology. The Great Filter suggests that there is a significant barrier preventing civilizations from advancing to the stage of interstellar travel and communication. This barrier could be biological, technological, or environmental, and it raises the unsettling possibility that humanity is either one of the few civilizations to have overcome the filter, or that the filter lies ahead, posing a threat to our future survival. The search for extraterrestrial life is, in part, a search for answers to this dilemma. Are we truly alone, or have other civilizations met their demise before they could reach the stars? As we look outward, we must also reflect on our ethical responsibilities. The possibility of colonizing other planets, such as Mars, raises important questions about our impact on the environment of these new worlds. If microbial life exists on Mars or elsewhere, what moral obligation do we have to protect it? Should we prioritize the survival of humanity above all else, or should we be stewards of other life forms, even if they are as simple as bacteria? These ethical dilemmas will become increasingly relevant as space exploration continues, and they challenge us to consider the broader implications of our actions in the universe. The exploration of space is not just about discovery, it is also about survival. As our planet faces environmental challenges such as climate change, resource depletion, and overpopulation, space offers a potential solution. The idea of becoming a multiplanetary species, as advocated by visionaries like Elon Musk, is driven by the belief that humanity must diversify its presence in the universe to safeguard against extinction. The colonization of Mars, the Moon, or other celestial bodies could serve as a backup plan for humanity in the event of a catastrophic event on Earth, such as a massive asteroid impact or a global pandemic. However, the notion of colonizing other planets brings with it a host of technical and societal challenges. Establishing a human presence on Mars, for example, would require overcoming significant obstacles, including the planet's harsh environment, low gravity, and thin atmosphere. Terraforming, the process of transforming a planet to make it more Earth-like, has been proposed as a long-term solution, but this idea remains speculative and would likely take centuries to achieve. In the meantime, human settlers on Mars would need to live in enclosed habitats, relying on advanced technology to provide air, water, and food. In addition to the technical challenges, there are social and political questions to address. How would governance work on a multiplanetary scale? Who would have the authority to make decisions about resource allocation and environmental protection on other planets? Would space colonies operate independently of Earth, or would they be subject to the laws and regulations of their home countries? These questions are still largely theoretical, but they will become increasingly relevant as space exploration progresses. While the idea of colonizing other planets captures the imagination, it is essential to recognize that space exploration offers benefits to life on Earth as well. Many of the technologies developed for space missions have practical applications in our daily lives. For example, advances in satellite technology have revolutionized communication, weather forecasting, and navigation. The development of lightweight materials and miniaturized electronics, driven by the need to reduce the weight and cost of spacecraft, has led to innovations in fields ranging from medicine to transportation. Moreover, space exploration has expanded our understanding of the universe in ways that were previously unimaginable. The study of black holes, neutron stars, and other exotic cosmic phenomena has provided insights into the fundamental laws of physics. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, have helped scientists refine their models of the universe's origin and evolution. The discovery of gravitational waves, ripples in space-time caused by the collision of massive objects, has opened up a new window for observing the universe, allowing us to hear the cosmos for the first time. As we push the boundaries of space exploration, the role of space agencies and international collaboration will continue to be critical. NASA, the European Space Agency, ESA, the Russian Space Agency Roscosmos, and the China National Space Administration, CNSA, among others, have made remarkable contributions to our understanding of space. However, space exploration is no longer the exclusive domain of government agencies. The rise of private companies like SpaceX, Blue Origin, and Rocket Lab is transforming the landscape of space travel, introducing new opportunities for innovation and reducing the costs associated with launching missions. The collaboration between public and private sectors is likely to define the future of space exploration. Government space agencies will continue to lead scientific research and long-term exploration missions, while private companies will drive innovation in areas such as commercial space travel, asteroid mining, and satellite deployment. Space tourism, once a distant dream, is now on the horizon, with companies like Virgin Galactic and Blue Origin offering suborbital flights to civilians. While still in its infancy, space tourism could become a significant industry in the coming decades, providing a new perspective on space for ordinary people. Looking further into the future, the possibilities of space travel are limited only by our imagination. Concepts that once seemed like science fiction, such as warp drives, wormholes, and space elevators, are being explored by scientists and engineers. While these ideas remain speculative, they inspire us to think beyond the confines of current technology and imagine what might be possible in the distant future. The development of advanced propulsion systems, such as ion drives or nuclear fusion engines, could one day make interstellar travel a reality, allowing us to explore planets orbiting distant stars. One of the most exciting frontiers in space exploration is the search for habitable exoplanets. The discovery of planets in the Goldilocks zone of their parent stars, where conditions are just right for liquid water to exist, has fueled hopes that we might one day find a second Earth. The James Webb Space Telescope, scheduled to launch in the coming years, will provide unprecedented insights into the atmospheres of exoplanets, potentially detecting signs of life. The search for biosignatures, chemical indicators of life, will be a key focus of future missions, as scientists work to answer one of humanity's oldest questions: are we alone in the universe? In addition to searching for life, future space missions will likely focus on the exploration of moons, asteroids, and comets within our solar system. Missions to Europa, Enceladus, and Titan, moons with the potential to harbor life, are in the planning stages. The exploration of asteroids and comets could provide clues about the early solar system and the origins of life on Earth. These small, icy bodies are thought to contain organic molecules, the building blocks of life, and studying them could help us understand how life emerged on our planet. While the exploration of space holds great promise, it also comes with risks and uncertainties. The hazards of space travel, including the potential for spacecraft malfunctions, radiation exposure, and collisions with space debris, are ever present. Space is a harsh and unforgiving environment, and even with the best technology, missions can go wrong. The loss of the Space Shuttle Challenger in 1986 and Columbia in 2003 are sobering reminders of the dangers inherent in space exploration. As we venture further into space, we must continue to prioritize safety and learn from past experiences. Beyond the technical and physical risks, space exploration also poses existential challenges. The discovery of intelligent extraterrestrial life, if it were to happen, would have profound implications for humanity. It would force us to rethink our place in the universe and could potentially disrupt religious, philosophical, and cultural beliefs. The famous Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them, remains one of the most intriguing puzzles in science. If intelligent life exists elsewhere, why haven't we found it yet? The answer to this question could have far-reaching consequences for our understanding of the universe and our future in space. As we look to the future of space exploration, it is clear that the next few decades will be a transformative period for humanity. The development of new technologies, the search for life, and the potential colonization of other planets will redefine our relationship with space. However, space exploration is not just about technology and science. It is also about imagination, curiosity, and the human spirit. It is a testament to our desire to explore the unknown, to push beyond our limits, and to seek answers to the most profound questions about existence. The journey into space is, in many ways, a journey inward. It challenges us to confront the limitations of our knowledge and the fragility of our existence. It forces us to ask difficult questions about our future and our responsibilities to one another and to the universe. As we continue to explore space, we must do so with humility, recognizing that we are but one small part of a vast, interconnected cosmos. Space exploration is not just about reaching for the stars, it is about understanding ourselves. It is about the drive to learn, to grow, and to expand our horizons. As we look up at the night sky, we are reminded that the universe is full of wonders waiting to be discovered. The stars beckon us to explore, to dream, and to imagine a future where humanity's reach extends beyond the boundaries of Earth. Space is the ultimate frontier, and our journey into the cosmos is only just beginning. This journey, however, is not without its challenges, and humanity must be prepared to face these trials head-on. The prospect of long-term space exploration brings forth a myriad of physiological and psychological issues that must be addressed before we can confidently venture beyond our planet for extended periods. One of the most pressing concerns is the impact of prolonged weightlessness on the human body. Astronauts aboard the International Space Station, ISS, experience significant physical changes during their missions, including muscle atrophy, bone density loss, and fluid redistribution that affects everything from their cardiovascular systems to vision. Without the constant pull of gravity, the body undergoes profound changes that can become serious over time. To mitigate these effects, scientists have developed rigorous exercise regimens for astronauts, utilizing resistance machines and stationary bikes. However, as missions extend beyond months and possibly into years, such as the proposed mission to Mars, more advanced solutions will be needed. Radiation is another critical challenge. Earth's magnetic field shields us from harmful cosmic radiation, but once we leave this protective bubble, astronauts are exposed to increased levels of radiation that can lead to cancer, neurological damage, and other serious health problems. Future spacecraft and space habitats will need to incorporate advanced shielding technologies to protect astronauts from these hazards. Research is ongoing into materials that can absorb or deflect radiation, as well as potential medical countermeasures that could help repair cellular damage caused by radiation exposure. Psychological challenges are equally significant. The isolation, confinement, and distance from Earth can take a toll on mental health, leading to feelings of loneliness, anxiety, and depression. Astronauts on long-duration missions are cut off from their families and friends, living in cramped quarters with little privacy. The isolation is even more profound on a mission to Mars, where communication with Earth could be delayed by up to 20 minutes one way. Maintaining crew morale and mental well-being in such environments will be crucial to the success of these missions. Research into mental health support, virtual reality environments to simulate familiar settings, and team-building exercises will all play a role in preparing astronauts for these extended missions. Beyond the physiological and psychological challenges, there are logistical hurdles that must be overcome for long-term space exploration to become a reality. Supplying astronauts with food, water, and oxygen for extended missions is a complex task, particularly when resupply missions from Earth are not an option. Current missions to the ISS rely on regular shipments from Earth, but this model will not be feasible for missions to the Moon, Mars, or beyond. To address this, space agencies are investigating the possibility of in-situ resource utilization, ISRU, which involves using local resources to support human life. On Mars, for example, scientists are exploring ways to extract water from the planet's soil and atmosphere, as well as produce oxygen from carbon dioxide using technology like NASA's MOXIE experiment. Growing food in space is another area of active research. While astronauts currently rely on prepackaged meals, fresh produce could provide important nutritional and psychological benefits on long-duration missions. Experiments aboard the ISS have shown that it is possible to grow plants in microgravity, but there are still many challenges to overcome, such as developing efficient systems for providing light, water, and nutrients in space environments. Hydroponics and aeroponics, which use water or air to deliver nutrients to plants without soil, are being tested as potential solutions for space farming. As we contemplate the possibility of establishing permanent settlements on other planets, the question of sustainability becomes paramount. Living off the land, so to speak, will be essential for survival on Mars or other celestial bodies. This could involve mining for resources such as metals and minerals, extracting water from ice deposits, and even developing closed-loop life support systems that recycle air, water, and waste. These technologies are still in their infancy, but they will be critical for ensuring the long-term viability of human settlements beyond Earth. In addition to these technological and logistical challenges, there are also ethical considerations that must be addressed as humanity expands its presence in space. The colonization of other planets raises questions about the impact on indigenous ecosystems, if they exist, and the ethical treatment of any life forms we may encounter. Even microbial life could hold immense scientific value, and our actions could inadvertently destroy evidence of extraterrestrial biology. The principle of planetary protection is already enshrined in space law, requiring that missions to other planets take steps to avoid contamination. But as our activities in space increase, so too will the ethical dilemmas we face. Private companies are also playing an increasingly prominent role in space exploration. The rise of commercial spaceflight, spearheaded by companies like SpaceX, Blue Origin, and others, is democratizing access to space and driving innovation. These companies are developing reusable rockets, space tourism ventures, and ambitious plans for colonizing Mars and establishing lunar bases. While this private sector involvement has the potential to accelerate progress, it also raises concerns about the commercialization of space and the concentration of power in the hands of a few wealthy individuals or corporations. As space becomes a new frontier for economic development, it will be important to ensure that the benefits are shared equitably and that space remains a global commons, accessible to all. Despite these challenges, the future of space exploration holds immense promise. Advances in technology, science, and international collaboration have brought us to the brink of a new era in space exploration. The next few decades could see humans walking on Mars, mining asteroids for valuable resources, and establishing permanent settlements on the Moon. Space tourism could become a reality for ordinary people, offering a new perspective on our place in the universe. One of the most exciting possibilities is the potential for breakthroughs in propulsion technology. Current spacecraft rely on chemical propulsion, which is relatively slow and limits our ability to explore distant planets and stars. However, new technologies, such as ion propulsion and nuclear fusion, could dramatically increase the speed and efficiency of space travel. Ion propulsion, already used on some spacecraft, accelerates ions to high speeds to generate thrust, allowing for longer missions with less fuel. Nuclear fusion, while still in the experimental stage, could provide an even more powerful and efficient means of propulsion, potentially making interstellar travel feasible. Looking further into the future, concepts like the Alcubierre warp drive, a theoretical propulsion system that could bend spacetime to allow faster-than-light travel, are being explored by scientists. While these ideas are still purely speculative, they capture the imagination and inspire us to think beyond the confines of our current technological limitations. If we can overcome the challenges of propulsion, we could one day send missions to explore exoplanets orbiting distant stars, searching for habitable worlds and perhaps even discovering alien life. The search for extraterrestrial intelligence, SETI, is another area that holds great potential for the future of space exploration. For decades, scientists have been scanning the skies for signals from alien civilizations, using radio telescopes and other instruments to listen for patterns that could indicate intelligent communication. While no definitive signals have been detected yet, the search continues, driven by the tantalizing possibility that we are not alone in the universe. Advances in technology, such as more sensitive detectors and more powerful telescopes, are increasing our ability to search for these signals. Additionally, the discovery of thousands of exoplanets has provided new targets for SETI researchers, increasing the likelihood that we may one day detect evidence of alien intelligence. As we move forward into this exciting new era of space exploration, it is important to remember that our journey into space is not just about science and technology. It is also about the human spirit, the desire to explore, to push beyond our limits, and to seek answers to the fundamental questions of existence. Space exploration is a reflection of our curiosity and our drive to understand the universe and our place within it. It is a testament to the power of human imagination and ingenuity, and it reminds us that, no matter how vast the cosmos may seem, we are capable of extraordinary things. As our journey into space continues, humanity must grapple with the profound implications of our expanding presence in the cosmos. Space exploration is not just a matter of technical achievement. It touches upon the philosophical, ethical, and existential questions that define who we are and who we aspire to become. As we venture further from Earth, we are forced to reconsider our place in the universe and the responsibilities that come with our growing capabilities. One of the most important questions we face is how we will balance the desire for exploration and colonization with the need for preservation. The idea of space as a new frontier evokes the same pioneering spirit that once drove the exploration of our own planet, but it also carries with it the potential for exploitation and harm. The Moon, Mars, and other celestial bodies are not lifeless wastelands to be conquered and consumed. They are unique environments with their own scientific value and potential for life. As we move toward the colonization of other worlds, we must ask ourselves, what is our ethical responsibility to preserve these environments for future generations? And how can we ensure that the mistakes of the past are not repeated on a cosmic scale? This question becomes even more pressing when we consider the potential discovery of extraterrestrial life. If we were to find microbial life on Mars, Europa, or Enceladus, it would represent one of the most significant scientific discoveries in human history. However, this discovery would also raise complex ethical dilemmas. Should we prioritize the survival of this alien life over our own ambitions for colonization? How do we balance the need for scientific research with the potential risks of contamination? These are not hypothetical questions. They are real issues that scientists, ethicists, and policymakers are already grappling with as space exploration moves forward. At the heart of these questions lies the concept of planetary protection. Planetary protection is the practice of preventing biological contamination of other planets and moons by Earth-based organisms, as well as protecting Earth from potential contamination by extraterrestrial life forms. The idea is to avoid the unintentional introduction of Earth life to other celestial bodies, which could disrupt their ecosystems and compromise scientific research. For example, if a human mission to Mars inadvertently introduced bacteria from Earth, it could be difficult, if not impossible, to determine whether any life forms found on the planet were indigenous to Mars or the result of contamination. This is why strict protocols are in place for space missions, particularly those involving the search for life. Robotic landers and rovers are meticulously sterilized before being sent to Mars or other potentially habitable worlds to minimize the risk of contamination. However, as human missions to Mars become more likely, the challenge of maintaining planetary protection becomes more complex. It is one thing to sterilize a robot, it is quite another to prevent human explorers, with all of their biological complexity, from inadvertently contaminating another planet. The question of contamination goes both ways. While the idea of bringing back samples from Mars or other planets is thrilling from a scientific perspective, it also raises concerns about the potential for harmful extraterrestrial organisms to be introduced to Earth. Though the risk is considered low, given what we currently know about the harsh conditions of space and the likelihood of life as we know it surviving such journeys, we cannot entirely rule out the possibility. As our exploration of the cosmos advances, so too must our protocols for ensuring the safety of both our planet and any other ecosystems we may encounter. Beyond the immediate ethical and environmental challenges, space exploration also forces us to confront deeper questions about the nature of life and our place in the universe. For centuries, humanity has looked up at the stars and wondered if we are alone. The search for extraterrestrial intelligence, SETI, is an ongoing effort to answer that question, and while we have yet to find definitive evidence of intelligent life beyond Earth, the sheer vastness of the universe makes the prospect of alien civilizations a tantalizing possibility. The discovery of intelligent extraterrestrial life would have profound implications for humanity. It would challenge our understanding of biology, culture, and even the concept of what it means to be human. How would we communicate with such beings, assuming we could even make contact? What would their technology, art, and philosophy look like? Would their existence fundamentally alter our own sense of identity and place in the cosmos? These are the questions that the discovery of intelligent life would force us to reckon with, and while the answers remain speculative, they underscore the far-reaching consequences of our search for life beyond Earth. Even in the absence of extraterrestrial civilizations, the exploration of space has already led to profound shifts in our worldview. The concept of the overview effect describes the cognitive shift experienced by astronauts when they view Earth from space. From this vantage point, the divisions and conflicts that dominate human society fade into insignificance, replaced by a sense of unity and interconnectedness. Many astronauts have reported feeling a deep sense of responsibility to protect the planet upon returning from space, recognizing the fragility of the biosphere and the interconnectedness of all life on Earth. This shift in perspective is not limited to astronauts. Space exploration has a way of broadening the collective human consciousness, encouraging us to think beyond the immediate concerns of our daily lives and consider the long-term future of our species. The famous pale blue dot image captured by the Voyager 1 spacecraft in 1990 serves as a powerful reminder of our place in the universe. In this image, Earth appears as a tiny, fragile speck suspended in the vastness of space. A mote of dust, as Carl Sagan described it. In a sunbeam, the pale blue dot has become a symbol of our shared responsibility to care for the planet and to recognize the interconnectedness of all life. This interconnectedness extends beyond Earth. As we venture further into space, we must consider the broader implications of our actions for the cosmos as a whole. The colonization of other planets, the mining of asteroids for resources, and the potential for interstellar travel all raise questions about our long-term role in the universe. Will humanity become a force for good in the cosmos, spreading knowledge, peace, and sustainability, or will we repeat the mistakes of our past, exploiting new worlds for profit and power without regard for the consequences? These are not just abstract questions. They are the kinds of dilemmas that future generations will have to grapple with as space exploration continues to advance. One of the most significant developments in space law will likely revolve around the issue of resource extraction. Asteroid mining, in particular, has the potential to revolutionize the global economy by providing access to vast quantities of precious metals, water, and other resources. Companies like Planetary Resources and Deep Space Industries have already begun exploring the feasibility of mining asteroids. And while the technology is still in its early stages, the potential rewards are enormous. However, this new frontier also raises concerns about the equitable distribution of resources and the environmental impact of mining operations in space. These questions of equity and sustainability will become even more pressing as space tourism and commercial space travel become more accessible. While the idea of ordinary people traveling to space is exciting, it also highlights the growing divide between those who can afford such experiences and those who cannot. The privatization of space travel raises questions about who has the right to access space and how we can ensure that space remains a domain for all of humanity, not just the wealthy elite. The development of international regulations and agreements will be essential in addressing these concerns and preventing the commercialization of space from exacerbating existing inequalities. Despite the challenges and uncertainties, space exploration represents one of the most exciting and transformative endeavors of our time. It is a testament to human ingenuity, curiosity, and the desire to explore the unknown. As we continue to push the boundaries of what is possible, we must do so with a sense of responsibility and foresight, recognizing that the decisions we make today will shape the future of humanity for generations to come. The journey into space is far from over. In fact, it has only just begun. From the Moon to Mars, from exoplanets to distant galaxies, the universe is full of wonders waiting to be discovered. Each new mission, each new discovery, brings us one step closer to understanding the true nature of the cosmos and our place within it. The stars beckon us to explore, to dream, and to imagine a future where humanity's reach extends beyond the confines of Earth. As we look to the skies, we are reminded that space is not just a destination, it is a reflection of our boundless potential and the infinite possibilities that lie ahead. As we venture deeper into space, we also confront a multitude of technological and logistical challenges that will determine the success or failure of our future endeavors. One of the most pressing concerns is the development of propulsion systems that can carry us farther and faster than ever before. While traditional chemical rockets have served us well for missions to the Moon, Mars, and the outer planets, they are inadequate for interstellar travel or long-duration missions to distant parts of our solar system. The vast distances involved in space exploration require us to think beyond current technology and develop new methods of propulsion that can enable us to reach the stars. One promising area of research is nuclear propulsion. Unlike chemical rockets, which rely on the combustion of fuel to generate thrust, nuclear rockets use nuclear reactions to produce energy. This energy can then be used to heat a propellant, such as hydrogen, to extremely high temperatures, creating a more efficient and powerful form of thrust. Nuclear thermal propulsion, for example, has the potential to significantly reduce the travel time to Mars, making human missions to the Red Planet more feasible. In addition, nuclear propulsion could open up the possibility of exploring the outer planets and their moons, which are currently beyond the reach of conventional propulsion systems. Another exciting development is the concept of ion propulsion. Unlike chemical or nuclear rockets, ion engines use electricity to accelerate charged particles, or ions, to produce thrust. While ion engines generate much lower levels of thrust than chemical rockets, they are far more efficient, allowing spacecraft to accelerate continuously over long periods. This makes ion propulsion ideal for deep space missions, where the primary challenge is not escaping Earth's gravity but traveling vast distances between celestial bodies. NASA's Dawn spacecraft, for example, successfully used ion propulsion to visit and study the asteroid Vesta and the dwarf planet Ceres, demonstrating the potential of this technology for future exploration. But even with advanced propulsion systems, the question of how to sustain human life on long-duration space missions remains a significant challenge. Space is an inherently hostile environment, with extreme temperatures, radiation, and the absence of gravity all posing serious risks to human health. One of the most pressing concerns is radiation exposure. Outside of Earth's protective atmosphere and magnetic field, astronauts are exposed to high levels of cosmic radiation, which can damage DNA and increase the risk of cancer and other health problems. protecting astronauts from this radiation is a major hurdle that must be overcome before we can send humans on long missions to Mars or beyond. Several potential solutions to this problem are being explored. One approach is to build spacecraft with thicker walls or use materials that are better at absorbing or deflecting radiation. Another idea is to create artificial magnetic fields around spacecraft, similar to Earth's magnetosphere, to shield astronauts from cosmic rays. Additionally, some scientists are researching the possibility of using pharmaceuticals to mitigate the effects of radiation exposure on the human body. While these solutions are still in the experimental stage, they represent important steps toward making long-duration space travel safer for humans. Another challenge is the issue of life support. On Earth, we take for granted the availability of air, water, and food, but in space, these resources must be carefully managed and recycled to sustain life over long periods. Current life support systems, such as those used on the International Space Station, ISS, are capable of recycling water and air to some extent, but they are not yet efficient enough to support a large crew on a multi-year mission. Developing closed-loop life support systems, in which waste products are continuously recycled into usable resources, is essential for long-term human presence in space. One area of research that holds promise in this regard is bioregenerative life support. This approach involves using plants, algae, and other biological organisms to recycle carbon dioxide, produce oxygen, and generate food for astronauts. Plants, for example, can convert carbon dioxide into oxygen through photosynthesis, while also providing a source of fresh food. Algae, on the other hand, can be used to produce oxygen and biomass, which can then be processed into food or other useful materials. These systems could potentially provide a self-sustaining environment for astronauts on long-duration missions, reducing the need for resupply missions from Earth. The challenges of space exploration extend beyond the technical and biological, however. There are also profound psychological and social issues that must be addressed if we are to successfully send humans on long-duration missions or establish colonies on other planets. Living in the confined and isolated environment of a spacecraft for months or years at a time can take a toll on mental health, leading to issues such as depression, anxiety, and interpersonal conflict. The psychological effects of space travel are a major area of concern for mission planners, particularly for missions to Mars, where astronauts would be isolated from Earth for years and would face significant delays in communication with mission control. To mitigate these risks, space agencies are conducting extensive research on the psychological and social dynamics of long-duration missions. Simulated Mars missions, such as the HIC's Hawaii Space Exploration Analog and Simulation Project, have been used to study how small groups of people cope with isolation and confinement over extended periods. These simulations provide valuable insights into the types of psychological support that will be needed for future missions, as well as the kinds of training and team-building exercises that can help astronauts work together effectively in high-stress environments. Additionally, there is growing interest in the role that virtual reality, VR, and artificial intelligence, AI, could play in supporting astronauts on long missions. VR could be used to create immersive environments that allow astronauts to take virtual vacations from the confines of their spacecraft, helping to reduce feelings of isolation and monotony. AI, on the other hand, could be used to provide personalized psychological support, offering real-time counseling and guidance to astronauts based on their individual needs. These technologies could play a crucial role in ensuring the mental well-being of astronauts on future deep space missions. As we look toward the future of space exploration, one of the most exciting possibilities is the prospect of interstellar travel. While the distances involved are staggering, Proxima Centauri, the nearest star to the Sun, is more than 4 light-years away. Scientists and engineers are already exploring concepts that could make interstellar travel a reality. One of the most ambitious proposals is the Breakthrough Starshot project, which aims to send tiny, light-powered spacecraft to Alpha Centauri, the closest star system to Earth, within the next few decades. These nanocrafts would be propelled by powerful lasers from Earth, allowing them to reach speeds of up to 20% the speed of light and complete the journey to Alpha Centauri in just over 20 years. While projects like Breakthrough Starshot are still in the early stages, they represent a bold vision for the future of space exploration, one in which humanity reaches beyond the solar system and begins to explore other star systems. The development of faster-than-light propulsion, though still purely theoretical, could one day make interstellar travel more feasible, opening up the possibility of visiting and even colonizing planets around other stars. In parallel with the quest for interstellar travel, scientists are also investigating the feasibility of creating artificial habitats in space. These space habitats, also known as space colonies, could provide a solution to the growing challenges of population growth and resource depletion on Earth. One of the most well-known concepts is the O'Neill cylinder, a massive rotating space station that would generate artificial gravity through centrifugal force. These habitats could be located in orbit around Earth, on the Moon, or in the asteroid belt, providing a new home for humanity beyond the confines of our planet. The construction of space habitats would require significant advancements in materials science, engineering, and robotics, but the potential benefits are enormous. In addition to providing new living spaces for a growing population, space habitats could serve as hubs for scientific research, resource extraction, and even tourism. They could also play a key role in the long-term survival of humanity, providing a backup plan in the event of a global catastrophe on Earth. As we push the boundaries of space exploration, we must also consider the potential for collaboration and competition between nations. Space has long been a domain of international cooperation, with the ISS serving as a symbol of what can be achieved when countries work together toward a common goal. One of the most debated issues is the question of resource extraction. As Earth's resources become increasingly strained, space mining, especially on asteroids, offers an enticing prospect for securing vital materials such as water, precious metals, and rare earth elements. Some asteroids are believed to contain trillions of dollars worth of metals like platinum and gold, and extracting water from these celestial bodies could enable the creation of fuel for long-duration missions, reducing the need to transport resources from Earth. However, without clear international agreements on how these resources can be exploited and who has the right to profit from them, there is a risk of a space rush, reminiscent of historical land and resource grabs on Earth, which could lead to conflict between nations and corporations. Furthermore, space exploration brings with it a set of environmental concerns. Space debris, or space junk, is already a growing problem in low Earth orbit, with thousands of defunct satellites, spent rocket stages, and fragments of spacecraft posing a risk to active satellites and future missions. As more satellites are launched into orbit, particularly with the rise of megaconstellations like SpaceX's Starlink, which aims to provide global internet coverage, the risk of collisions and the creation of more debris increases. Scientists are already warning of a potential Kessler syndrome, a scenario in which the density of objects in orbit becomes so high that collisions between them generate an ever-growing cloud of debris, making space travel and satellite operations increasingly dangerous or even impossible. Addressing the issue of space debris will require international cooperation, innovative technology for debris removal, and stricter regulations on satellite deployment and end-of-life disposal. In addition to debris management, the environmental impact of launching rockets from Earth is another concern. Rockets produce large amounts of carbon emissions and other pollutants, contributing to climate change and atmospheric damage. While the number of rocket launches is relatively small compared to other sources of pollution, the growth of the space industry, with more frequent launches, could exacerbate these effects. Some companies are already working on more environmentally friendly launch technologies, such as reusable rockets or rockets that use less polluting fuels. But the environmental cost of space exploration remains a topic of ongoing debate. On a more existential level, the exploration and potential colonization of space forces humanity to confront profound questions about our place in the universe. For millennia, we have looked to the stars with wonder and curiosity, seeing them as distant and unreachable. Now, as we prepare to take our first steps toward becoming a multiplanetary species, we must grapple with the implications of this shift in perspective. What does it mean to extend human civilization beyond Earth? How will our culture, values, and identities evolve in response to life on other planets or in artificial habitats in space. Some philosophers and scientists argue that space colonization represents the next logical step in human evolution, a way for our species to ensure its survival in the face of existential risks like climate change, nuclear war, or asteroid impacts. Others, however, caution against viewing space as an escape plan or a backup Earth. They argue that we have a moral obligation to take care of our home planet and address the challenges we face here before looking to other worlds. There is also the concern that space colonization could exacerbate existing inequalities on Earth, with the wealthy and powerful gaining access to space-based resources and opportunities, while the rest of humanity is left behind. The search for extraterrestrial life is another aspect of space exploration that has profound implications for humanity. For decades, scientists have been scanning the skies for signals from intelligent civilizations and searching for evidence of microbial life on planets like Mars and the moons of the outer planets, such as Europa and Enceladus. While we have yet to find definitive proof of life beyond Earth, the discovery of even the simplest microorganisms would be one of the most significant scientific breakthroughs in history. It would challenge our understanding of biology, evolution, and the uniqueness of life on Earth. More importantly, it would raise fundamental questions about the nature of life itself and our place in the cosmos. If we were to discover intelligent extraterrestrial life, the implications would be even more profound. How would we communicate with a civilization that might be millions of years more advanced than us, or one that is fundamentally different in its biology, culture, and technology? What ethical considerations would come into play in our interactions with extraterrestrial beings? Should we attempt to make contact at all, or is there a risk that doing so could lead to unintended consequences, such as the inadvertent introduction of harmful pathogens or cultural misunderstandings that could escalate into conflict? Even in the absence of direct contact with extraterrestrial civilizations, the search for life elsewhere in the universe can help us reflect on our own humanity. It prompts us to consider what it is that makes life valuable, what our responsibilities are to other forms of life, and how we should approach the possibility of sharing the cosmos with other intelligent beings. At the same time, the exploration of space offers us a unique vantage point from which to view Earth itself. Astronauts who have traveled to space often speak of the overview effect, a profound cognitive shift that occurs when they see Earth from the vantage point of space. From this perspective, national borders disappear, and the planet is seen as a fragile, interconnected whole. The overview effect has inspired many astronauts to become advocates for environmental conservation, peace, and international cooperation, as they return to Earth with a renewed sense of the importance of protecting our home planet. As humanity looks to the stars, we must not lose sight of the challenges we face here on Earth. The pursuit of space exploration should not come at the expense of addressing pressing issues like climate change, poverty, and inequality. Instead, it should be seen as part of a broader effort to expand human knowledge, improve our technological capabilities, and secure a sustainable future for all. Space offers us not only the potential for scientific discovery and technological advancement, but also the opportunity to reflect on who we are, where we come from, and where we are going as a species. In the coming decades, we will likely witness some of the most transformative developments in the history of space exploration. Human missions to Mars, the construction of space habitats, and the discovery of life on other worlds are all within the realm of possibility. These achievements will undoubtedly bring new challenges and opportunities, as well as new ethical and philosophical questions that we must confront. But if history has taught us anything, it is that humanity is capable of rising to the occasion and meeting the challenges of exploration and discovery. Space exploration is not just about science and technology. It is about the human spirit, our innate curiosity, our drive to explore the unknown, and our desire to push the boundaries of what is possible. As we embark on this next phase of our journey into the cosmos, we are not just exploring new worlds. We are exploring the very limits of our potential as a species. And in doing so, we are ensuring that the legacy of humanity will endure, not just on Earth, but among the stars. As we continue our quest into the cosmos, the potential for humanity's presence beyond Earth becomes ever more tangible, but this path is fraught with complexities. One of the most pressing long-term questions facing us is how to establish sustainable human life in space. If we are to thrive off Earth, whether on the Moon, Mars, or aboard colossal space stations, we will need to devise innovative systems that can provide reliable sources of food, water, energy, and shelter. Terraforming, the hypothetical process of altering a planet's environment to make it habitable for Earth-like life, has long been a topic of science fiction. However, as our understanding of planetary science grows, so too does the scientific discussion around the feasibility of such an endeavor. Mars is frequently cited as a candidate for terraforming, given its similarities to Earth, such as its day length and polar ice caps. Ideas for transforming Mars into a more Earth-like world range from the introduction of greenhouse gases to warm the planet, to the use of giant mirrors in space to reflect sunlight onto its surface. These concepts, while exciting, remain speculative and would require centuries, if not millennia, to bring to fruition, if they are possible at all. In the meantime, we must focus on more immediate methods of ensuring survival on other worlds. For Mars, this means developing habitats that can protect astronauts from the planet's harsh conditions, including its low temperatures, thin atmosphere, and high levels of radiation. Underground habitats, shielded by layers of Martian soil, are one possibility. Another is the construction of domes or inflatable habitats that could house self-contained ecosystems. In such environments, advanced life support systems would recycle air, water, and waste, creating a closed-loop system that mimics Earth's natural cycles. The challenge of growing food in space is also an area of active research. NASA and other space agencies have already experimented with growing plants aboard the International Space Station, ISS, and future missions will build on these experiments to develop more robust space agriculture systems. Hydroponics and aeroponics, methods of growing plants without soil, are especially promising for space environments. These techniques use less water than traditional agriculture and can be adapted to the microgravity conditions of space or the low gravity of other planets. Additionally, genetic engineering may play a role in developing crops that are better suited to the unique conditions of space or extraterrestrial environments. The Moon offers a more immediate testing ground for many of these technologies. With NASA's Artemis program planning to return humans to the lunar surface in the coming years, the Moon could serve as a proving ground for technologies that will eventually be used on Mars and beyond. The establishment of a permanent lunar base could provide valuable insights into the challenges of living and working in space over extended periods. The Moon's proximity to Earth makes it an ideal location for testing closed-loop life support systems, new energy sources, and sustainable building materials, all of which will be critical for future missions to Mars and beyond. In parallel with these efforts, there is growing interest in the potential for in-situ resource utilization, ISRU, which refers to the use of materials found on other planets or moons to support human missions. Rather than transporting all the resources needed for a mission from Earth, ISRU would allow astronauts to live off the land by extracting water, oxygen, and other essential materials from the environments they are exploring. On Mars, for example, scientists are exploring ways to extract water from the planet's subsurface ice deposits and to generate oxygen from the carbon dioxide in the Martian atmosphere. Similarly, the Moon's surface is rich in resources such as water ice, which could be used to produce fuel and drinking water for lunar missions. Energy is another critical concern for long-term space exploration. While solar power is a reliable source of energy for spacecraft and space stations in orbit, its effectiveness diminishes as we move farther from the Sun. On Mars, for example, dust storms can obscure sunlight for weeks or even months, making solar power unreliable. Nuclear power, particularly small modular reactors, offers a potential solution to this problem. These reactors could provide a steady and reliable source of energy for lunar or Martian bases, powering life support systems, scientific experiments, and manufacturing processes. NASA and the U.S. Department of Energy are currently working on the development of a nuclear reactor for use in space, with the goal of deploying it on the Moon in the near future. The ability to manufacture tools, equipment, and even habitats using local materials is another area of research with significant implications for space exploration. 3D 3D printing, or additive manufacturing, has already been tested on the ISS, and future missions could use this technology to produce everything from spare parts to entire buildings. On the Moon or Mars, 3D printing could be used to create habitats from regolith, the loose soil and rock that covers the surface of these celestial bodies. By using local materials, astronauts would be less reliant on resupply missions from Earth, reducing costs and increasing the self-sufficiency of space colonies. While the technological challenges of establishing human life in space are immense, they are not insurmountable. However, as we move closer to realizing this goal, we must also consider the ethical implications of space colonization. One of the central ethical questions is whether we have the right to alter other worlds for our own purposes. If life, either microbial or more complex, exists on Mars or other celestial bodies, what responsibilities do we have to protect it? Should we refrain from terraforming or other activities that could harm potential alien ecosystems, even if it means limiting our ability to settle these worlds? Moreover, the social and political dimensions of space colonization must be carefully considered. Who will have access to space, and who will be excluded? Will space become the domain of a wealthy elite, leaving the rest of humanity behind on an increasingly strained and resource-depleted Earth? Or can space exploration be pursued in a way that benefits all of humanity, ensuring that the wealth and knowledge gained from space are shared equitably? The potential for space colonization also raises questions about the kind of societies we want to build on other worlds. Will space colonies mirror the political, social, and economic systems of Earth, or will they represent an opportunity to create new forms of governance and social organization? Some visionaries have suggested that space colonization offers a chance to experiment with new forms of democracy, economics, and community that are more sustainable and just than those on Earth. Others, however, warn that space colonies could become dystopian enclaves of exploitation and inequality, where workers are subjected to harsh conditions while a small elite profits from their labor. As we stand on the cusp of becoming a multiplanetary species, we must grapple with these ethical, social, and political questions. The decisions we make in the coming decades will shape not only the future of space exploration, but also the future of humanity itself. Will we approach space with the same competitive, extractive mindset that has driven much of human history on Earth, or will we take this opportunity to redefine our relationship with each other and with the universe? In many ways, space exploration forces us to confront the fundamental questions of what it means to be human. The desire to explore, to push beyond the boundaries of the known, is deeply ingrained in our species. It is a drive that has taken us from the plains of Africa to the moon, and it will undoubtedly take us even farther in the centuries to come. But as we venture into the cosmos, we must also remember that exploration is not just about the discovery of new places, it is also about the discovery of ourselves. What kind of future do we want to build, not just on other planets, but here on Earth? How will the lessons we learn in space change the way we live on our home planet? Space offers us a new perspective on these questions, a chance to see ourselves and our world from a vantage point that is both awe-inspiring and humbling. It is a reminder that, in the grand scheme of the universe, we are all connected, part of a single fragile ecosystem in the vastness of space. In the end, space exploration is more than just a technological challenge, it is a moral and philosophical journey. It is a journey that will test not only our engineering skills but also our values, our vision, and our capacity for compassion and cooperation. And it is a journey that will ultimately define the future of humanity, not just as inhabitants of Earth, but as citizens of the cosmos. As humanity stands on the precipice of this new era, the prospect of space exploration takes on an even deeper meaning, transcending the purely scientific and technological. It becomes a question of identity, of what we as a species are capable of, and what we hope to achieve in the long run. Space exploration forces us to consider how we can move beyond our current limitations, not only in terms of our physical capacities but also in terms of our philosophical and ethical frameworks. One of the key lessons we can draw from our history is the importance of inclusivity. Just as the early explorers of Earth's oceans and continents were often driven by the ambitions of a few powerful nations, today's space exploration is largely dominated by a handful of governments and private companies. This raises important questions about who gets to participate in the exploration and settlement of space, and who is left out. As space exploration becomes more commercialized, with private companies like SpaceX and Blue Origin playing a leading role, the risk of exclusion grows. Will the future of space be shaped solely by those with the financial means to invest in it? Or can we ensure that the benefits of space exploration are shared by all? The concept of space as a global commons, a resource that belongs to all of humanity, is enshrined in international law, particularly in the 1967 Outer Space Treaty. But as space becomes more crowded, and as more actors seek to claim a piece of it, this principle is coming under strain. How do we ensure that space remains accessible to all nations, regardless of their economic or technological capabilities? How do we prevent the monopolization of space resources by a few powerful entities? These are questions that the global community will need to address in the coming years, as space exploration moves from the realm of government-led missions to a more commercialized and competitive landscape. Moreover, the ethics of space exploration go beyond questions of access and ownership. They also encompass how we interact with the environments we explore. If we discover life on other planets or moons, what responsibilities do we have to protect it? Should we prioritize the search for extraterrestrial life, or focus on the needs of human colonization? These are not just scientific questions, they are moral dilemmas that will shape the future of space exploration. The discovery of even microbial life on Mars, Europa, or elsewhere in our solar system would challenge many of our assumptions about the uniqueness of life on Earth, and would force us to reconsider our role in the universe. The possibility of encountering intelligent extraterrestrial life brings even greater ethical complexities. The famous Fermi paradox, the question of why, given the vastness of the universe, we have not yet encountered evidence of other advanced civilizations, remains one of the most intriguing puzzles in science. Some theories suggest that intelligent life is exceedingly rare, while others propose that civilizations may destroy themselves before they achieve interstellar communication. If we ever do make contact with an intelligent extraterrestrial species, the consequences could be profound, reshaping our understanding of civilization, technology, and even our place in the cosmos. But it could also bring risks. What if such a civilization is hostile, or if the mere act of contact causes unintended harm to either party? In the face of these uncertainties, the search for extraterrestrial life offers a humbling reminder of the fragility of life on Earth. It forces us to confront the possibility that we may be alone in the universe, or that we may be one of many civilizations, separated by vast distances of time and space. Either scenario is awe-inspiring, and both have the potential to reshape human culture in profound ways. If we are alone, then the responsibility to protect and preserve life on Earth becomes even more pressing. If we are not alone, then the challenge of coexisting with other intelligent beings in the universe will require new levels of diplomacy, empathy, and understanding. Yet even as we look outward, toward the possibility of life beyond Earth, we must not forget the importance of life here at home. The exploration of space has always been deeply intertwined with the exploration of Earth. From the first images of our planet taken by astronauts aboard the Apollo missions to the continuous monitoring of Earth's climate by satellites in orbit, space exploration has given us new tools for understanding and protecting our world. As we face the growing threats of climate change, environmental degradation, and resource scarcity, space technology offers new ways of addressing these challenges. Satellites provide critical data for monitoring weather patterns, tracking deforestation, and managing natural resources. Space-based solar power, asteroid mining, and other technologies hold the promise of alleviating some of the pressures on Earth's ecosystems. However, the relationship between space and Earth is not just one of technology and resources, it is also one of perspective. The overview effect, experienced by astronauts, in which seeing Earth from space gives them a profound sense of the interconnectedness and fragility of life, offers an important lesson for all of us. As we venture farther into the cosmos, we are reminded of how small and precious our planet truly is. This shift in perspective can inspire new forms of environmental stewardship, global cooperation, and a renewed commitment to addressing the challenges we face on Earth. Space exploration, in this sense, is not just about the future, it is about the present. It challenges us to think beyond our immediate concerns and to consider the long-term survival of our species. It forces us to confront the limits of our current understanding and to push beyond them in search of new knowledge, new possibilities, and new ways of living. But it also reminds us of the importance of taking care of the only home we have ever known. As we move forward into this new era of exploration, we must ask ourselves what kind of future we want to create. Will we use space as a platform for cooperation and shared progress, or will it become another arena for competition and conflict? Will we approach other worlds with a sense of responsibility and respect, or will we repeat the mistakes of our past explorations on Earth? These questions are not just for scientists, engineers, or policymakers. They are questions for all of humanity. They require us to think deeply about our values, our priorities, and our vision for the future. In the end, space exploration is about more than just the discovery of new worlds. It is about the discovery of ourselves. It is an opportunity to reflect on who we are, where we come from, and where we are going as a species. It is a chance to push the boundaries of human potential and to explore the very limits of our existence. And it is a reminder that, no matter how far we travel, we are all part of a single, fragile ecosystem, floating in the vastness of space. The journey into the cosmos is just beginning. What we discover out there will undoubtedly reshape our understanding of the universe and our place within it. But perhaps the most important discoveries will not be about distant stars or alien worlds. They will be about ourselves, and the kind of future we choose to create for generations to come. As we extend our gaze into the future of space exploration, the scope of humanity's ambitions expands beyond mere survival. The stars call to us not just as a challenge, but as an opportunity to redefine what it means to thrive. While the early phases of space exploration focus on overcoming basic hurdles, habitation, resource generation, and sustainability, our long-term vision for space is much grander. The dream of becoming an interplanetary species is only the first step. Beyond that, there lies the idea of building entire civilizations across the solar system, and, eventually, beyond. This future raises profound questions about the evolution of human culture, governance, economics, and even biology in space. The concept of space megastructures, such as O'Neill's cylinders, Stanford toruses, or Dyson spheres, provides a glimpse into what these future civilizations might look like. O'Neill's cylinders, for instance, are massive rotating habitats that could simulate gravity through centrifugal force, housing millions of people in environments similar to Earth's surface. These space colonies could exist in stable orbits around planets, or in more distant parts of the solar system, perhaps even in the asteroid belt, or in orbit around gas giants like Jupiter or Saturn. These structures would be self-contained worlds, with their own ecosystems, energy sources, and economies. A Dyson sphere, or its more achievable variant, a Dyson swarm, represents an even more ambitious idea: the harnessing of a star's entire energy output to power a civilization. This concept, first proposed by physicist Freeman Dyson, suggests surrounding a star with a vast array of solar panels or habitats, capturing all the energy it emits. While the construction of such a structure is far beyond our current technological capabilities, it provides a framework for thinking about the ultimate energy solutions that an advanced space-faring civilization would need. Energy is, after all, the lifeblood of any society, and the ability to capture and use energy on a massive scale will be crucial as humanity moves deeper into space. But what would life be like for the people living in these futuristic space habitats? The experience of living in space will undoubtedly differ in profound ways from life on Earth. The challenges of isolation, limited resources, and environmental control will shape the cultures that emerge in space colonies. The psychological effects of living in an artificial environment, with a limited horizon and no natural sky, could lead to entirely new forms of art, philosophy, and spirituality. Moreover, as different space colonies evolve in isolation from one another and from Earth, we may see the emergence of diverse cultures and societies, each adapted to its specific environment. Just as Earth's continents gave rise to unique civilizations with their own languages, traditions, and ways of life, space may give birth to entirely new forms of human existence. The prospect of biological evolution in space is another fascinating dimension of this future. Humans are products of Earth's environment, shaped by billions of years of evolution under specific conditions: gravity, atmospheric pressure, radiation levels, and the presence of water, among others. In space, these conditions will change, sometimes dramatically. In low-gravity environments, for example, the human body experiences muscle atrophy, bone density loss, and changes in fluid distribution. Over generations, it is conceivable that humans born and raised in space could develop physiological traits different from those of Earth-bound humans. Perhaps future space dwellers will evolve to be taller and more slender, with elongated limbs to adapt to low-gravity conditions. Or they may develop enhanced resistance to radiation, a constant threat in the vacuum of space. Beyond natural evolution, the possibilities of genetic engineering, cybernetic enhancement, and artificial intelligence integration open the door to even more radical transformations of the human species. As we gain greater control over our biology through CRISPR and other gene editing technologies, we may choose to modify ourselves to better suit life in space. These changes could range from minor adjustments, such as increased resistance to radiation or improved bone density, to more profound alterations, such as the ability to breathe different atmospheric compositions or survive in extreme temperatures. As our understanding of neuroscience and artificial intelligence advances, we may also explore the integration of technology into our bodies in new and unprecedented ways, augmenting our cognitive and physical abilities to adapt to the rigors of space exploration. The ethical implications of such changes are vast. How will society navigate the potential divide between enhanced humans and those who remain biologically unchanged? Could this lead to new forms of inequality, or even to entirely new species of humans with vastly different abilities and life experiences? The future of space exploration may involve not only the expansion of human civilization across the cosmos, but also the diversification of what it means to be human. And what of artificial intelligence itself? As space exploration becomes more automated, with robots and AI systems taking on increasingly complex tasks, we must consider the role that these entities will play in our future society. Autonomous AI systems could be critical to the success of space missions, managing life support systems, conducting scientific research, and even constructing habitats in environments that are too hostile for humans. In the long term, AI may evolve into something more than just a tool, perhaps even becoming partners or companions to human explorers. Some futurists predict that AI could eventually surpass human intelligence, leading to a singularity, in which humans and machines merge to form a new kind of hybrid civilization. The idea of a space-faring civilization of humans and AI working together to explore the cosmos raises deep philosophical questions about the nature of consciousness, intelligence, and the human experience. If we create machines that can think, learn, and perhaps even feel, do they deserve the same rights and protections as humans? And if AI systems become more advanced than us, what role will we play in this new hierarchy? Will we remain the masters of our creations? Or will we need to find new ways to coexist with beings of equal or greater intelligence? These are questions that humanity must grapple with as we move toward a future where space exploration and artificial intelligence are deeply intertwined. Another fascinating aspect of this future is the potential for interstellar travel. While the colonization of the Moon, Mars, and other bodies within our solar system is within reach in the coming decades, the idea of traveling to other star systems is still in the realm of speculation. The vast distances between stars, measured in light years, make interstellar travel a monumental challenge. Even the nearest star system, Alpha Centauri, is over 4 light-years away, meaning it would take tens of thousands of years to reach it using current propulsion technology. However, scientists and engineers are exploring a variety of concepts for faster-than-light travel or near-light-speed travel. One idea is the development of advanced propulsion systems, such as nuclear fusion or antimatter engines, which could accelerate spacecraft to a significant fraction of the speed of light. Another concept is the use of warp drives or wormholes, which, while purely theoretical at this point, offer the tantalizing possibility of bypassing the limitations of conventional space travel by warping spacetime itself. If such technologies were to become feasible, they would open up the entire galaxy to exploration and colonization, dramatically expanding the horizons of human civilization. The discovery of habitable exoplanets, planets orbiting stars outside our solar system, adds to the allure of interstellar travel. With the help of telescopes like NASA's Kepler and James Webb Space Telescopes, astronomers have identified thousands of exoplanets, some of which lie in the habitable zone, where conditions might be right for life. The dream of one day traveling to these distant worlds, exploring their landscapes, and perhaps even discovering alien life is one of the most compelling drivers of space exploration. Yet, the journey to the stars will not be easy. The technical challenges of building spacecraft capable of surviving the trip, maintaining life support for generations of travelers, and navigating the vastness of interstellar space are immense. Even more challenging are the social and psychological challenges of living in isolation for extended periods. If we ever undertake interstellar missions, they may need to be multi-generational, with the descendants of the original crew continuing the journey long after their forebears have passed away. The idea of spending one's entire life aboard a spacecraft, knowing that you will never set foot on Earth again, and that the destination is far beyond your lifetime, is a profound shift in how we think about exploration. However, if humanity can overcome these challenges, the rewards will be immeasurable. Interstellar travel would not only allow us to explore new worlds, but also provide insurance for the survival of our species. If a catastrophe were to befall Earth, or even our solar system, having colonies in other star systems would ensure that humanity endures. In this sense, interstellar travel is not just about curiosity or ambition, it is about the long-term survival of life as we know it. As we contemplate the vastness of space and the future of humanity among the stars, we are reminded of how far we have come and how much further we have to go. The journey of space exploration, from the first tentative steps on the moon to the bold visions of interstellar travel, is a testament to human ingenuity, resilience, and our insatiable desire to explore the unknown. Each new discovery, each new milestone, brings us closer to a future where the cosmos is not just a distant dream but a living reality, filled with possibilities that stretch the imagination and challenge the very limits of what we know. The road ahead is long, filled with both triumph and challenge, but the destination, a universe waiting to be explored, is more than worth the effort. In the grand tapestry of existence, humanity's role in space is only beginning to unfold, and the chapters yet to be written will define not just the future of our species, but the future of life itself, as it reaches out to touch the stars. As humanity's gaze continues to shift from our immediate surroundings to the vast expanse of space, the vision of a truly interstellar civilization begins to crystallize. Such a future, while still far off, beckons us to imagine the implications of becoming a multi-planetary species and beyond. The challenges and opportunities of this endeavor will redefine our relationship with the universe, fundamentally altering how we perceive our place in it and how we interact with the cosmos. The journey towards becoming an interstellar civilization involves several key stages, each of which presents its own set of scientific, technological, and philosophical challenges. The first stage is the establishment of permanent human settlements on the Moon and Mars. These endeavors are not just about setting foot on new worlds, but about creating self-sustaining environments that can support human life over the long term. The success of these projects will depend on our ability to develop and deploy advanced technologies that can handle the harsh conditions of space and alien environments. Life on the Moon and Mars will necessitate the development of new forms of habitat construction, energy generation, and resource management. Lunar bases might leverage local resources to create habitats that are shielded from radiation, capable of sustaining life in the vacuum of space. Martian colonies will face even more complex challenges, including the need to terraform parts of the planet to create a more Earth-like atmosphere and climate. Innovations in agriculture, waste management, and life support systems will be critical to ensuring that these colonies can thrive. Moving beyond the Moon and Mars, The next stage involves the exploration and potential colonization of the outer planets and their moons. The gas giants, Jupiter, Saturn, Uranus, and Neptune, present unique opportunities for exploration due to their diverse and complex systems. For instance, Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust, which could harbor life. Similarly, Saturn's moon Titan has a thick atmosphere and liquid lakes of methane and ethane, offering intriguing possibilities for scientific discovery and potential human settlement. Building habitats in the outer solar system will require advances in propulsion technology to reduce travel times and improve efficiency. Concepts such as nuclear propulsion or ion drives could make these long journeys more feasible. Additionally, developing technologies to protect humans from the increased radiation and extreme temperatures of these outer regions will be crucial for any long-term habitation efforts. The ultimate frontier lies in the realm of interstellar travel, the pursuit of reaching other star systems. The immense distances involved mean that even with the fastest spacecraft we can currently conceive, journeys to nearby stars would take decades or even centuries. To overcome this, researchers are exploring several cutting-edge concepts. One such concept is the Breakthrough Starshot Initiative, which proposes using powerful lasers to propel tiny, lightweight spacecraft to a significant fraction of the speed of light. This would potentially enable probes to reach the Alpha Centauri system within a few decades, sending back invaluable data about our nearest stellar neighbors. Another intriguing concept is the use of generational ships, massive spacecraft designed to support human life for multiple generations. These ships would be self-contained, with closed-loop life support systems that recycle air, water, and nutrients. The inhabitants of these ships would live out their entire lives in space, with the goal of reaching distant star systems long after their descendants have taken over. The societal, psychological, and logistical aspects of living on such a vessel pose significant challenges, from maintaining mental health in isolation to ensuring social cohesion over long periods. The search for exoplanets, planets orbiting stars outside our solar system, continues to yield promising results. Advances in telescope technology have allowed scientists to detect and study exoplanets with increasing precision. The discovery of Earth-like planets in the habitable zones of their stars raises the possibility of finding worlds that could support life. Missions such as the James Webb Space Telescope aim to characterize the atmospheres of these planets, looking for signs of habitability or even biomarkers that could indicate the presence of life. The potential discovery of extraterrestrial life would be one of the most profound scientific achievements in human history. It would not only answer questions about whether we are alone in the universe but also provide insights into the conditions that foster life. As we move further into the future, the integration of artificial intelligence and robotics will play a crucial role in advancing space exploration. Autonomous systems could take on a wide range of tasks, from performing complex scientific experiments to constructing habitats and infrastructure on distant worlds. AI could also assist in navigating the challenges of space travel, optimizing resource usage, and managing the health and safety of human crews. The synergy between human ingenuity and machine intelligence will likely be a defining feature of future space missions. The development of a spacefaring civilization will also bring about new economic opportunities. The commercialization of space, including space tourism, asteroid mining, and the development of off-world industries, could create new markets and drive economic growth. Space tourism, for example, is already on the horizon, with private companies working to make suborbital and orbital flights accessible to civilians. The potential for mining asteroids for valuable minerals could revolutionize resource extraction and supply chains on Earth. However, these advancements come with their own set of challenges. The ethical framework governing space activities will need to evolve to address issues such as property rights, environmental protection, and the management of space debris. International cooperation and regulation will be essential to ensure that space remains a domain for peaceful exploration and scientific advancement, rather than becoming a battleground for territorial disputes or resource conflicts. As we look to the stars, we are also reminded of the profound philosophical questions that space exploration raises. The quest for knowledge and the drive to explore the unknown are deeply ingrained in the human spirit. They reflect our curiosity, our desire to understand our place in the universe, and our aspiration to reach beyond our immediate limitations. Space exploration challenges us to think about the long-term future of our species, the potential for life beyond Earth, and the ethical considerations of our actions as we venture into the cosmos. The journey to becoming an interstellar civilization is a journey of transformation, of technology, society, and our very understanding of what it means to be human. It is a quest that will require collaboration, innovation, and resilience. As we embark on this extraordinary adventure, we are not only exploring new frontiers but also redefining the boundaries of human potential. In the end, the exploration of space is not just about reaching new worlds or discovering new forms of life. It is about expanding the horizons of human experience and understanding, pushing the limits of our imagination, and forging a future where the possibilities are as boundless as the universe itself. The cosmos invites us to dream big, to reach for the stars, and to embrace the infinite potential that lies beyond our current knowledge. As we continue to explore and innovate, we carry with us the hopes and dreams of generations past and the promise of a brighter future for all of humanity. As we venture further into the realm of space exploration and the possibilities of becoming a truly interstellar species, we are confronted with an array of profound and intricate considerations. The very fabric of our civilization may undergo transformations that are both exhilarating and challenging as we tackle the tasks of extending our reach beyond the confines of our home planet. One of the most captivating aspects of this future is the potential for human colonization of other star systems. The challenges involved in such an endeavor are immense, from developing the technology needed for interstellar travel to ensuring the sustainability of life over potentially centuries-long journeys. The prospect of establishing colonies in distant star systems is not just about reaching new destinations but also about creating thriving, self-sustaining communities that can flourish far from Earth. Building such colonies will require breakthroughs in many fields. For instance, the development of advanced propulsion systems will be crucial. Concepts such as the solar sail, which uses the pressure of sunlight for propulsion, and nuclear fusion, which offers the promise of almost limitless energy, are among the most promising approaches currently under exploration. While the engineering challenges are formidable, these technologies hold the potential to drastically reduce travel times and make interstellar missions more feasible. Furthermore, the concept of generation ships, massive vessels designed to support human life for extended periods, presents both fascinating possibilities and daunting challenges. These ships would be self-contained ecosystems, with advanced systems for recycling air, water, and nutrients, as well as methods for producing food and energy. The social dynamics of life aboard a generation ship would be complex, requiring careful planning to ensure the well-being and productivity of its inhabitants. Issues such as governance, education, and mental health will need to be addressed to maintain a harmonious and effective society over multiple generations. In addition to these technological and social challenges, there are also ethical and philosophical considerations. The colonization of other star systems raises questions about our responsibility as explorers. What rights do we have to alter or inhabit other worlds? How do we ensure that our activities do not cause harm to any potential extraterrestrial ecosystems or civilizations? These questions will require thoughtful and deliberate consideration as we move forward. One of the most profound implications of interstellar exploration is the potential discovery of extraterrestrial life. The search for alien life is one of the most exciting aspects of space exploration, and the potential discovery of life beyond Earth would have far-reaching implications for our understanding of the universe and our place within it. The identification of microbial life on a distant planet or moon could provide insights into the conditions that foster life and help us understand the potential for life elsewhere in the galaxy. As we continue to explore the cosmos, the role of artificial intelligence and robotics will become increasingly important. These technologies are already playing a crucial role in space missions, from rovers exploring the surface of Mars to telescopes probing the depths of the universe. In the future, AI and robotics will be essential for managing the complex tasks required for deep space exploration, from operating spacecraft to conducting scientific research. The integration of AI into space missions offers numerous benefits, including enhanced data analysis, improved decision-making, and the ability to perform tasks that are too dangerous or complex for humans. However, it also raises important questions about the nature of intelligence and the ethics of creating autonomous systems. As AI continues to advance, it will be crucial to address these issues and ensure that the technology is used responsibly and ethically. Another significant consideration for the future of space exploration is the potential for space commercialization. The development of space tourism, asteroid mining, and other commercial ventures could open new economic opportunities and drive innovation in the space industry. Space tourism, in particular, has the potential to make space more accessible to a broader range of people, providing a unique and transformative experience for those who venture beyond our planet. Asteroid mining, on the other hand, could revolutionize resource extraction by providing access to valuable minerals and materials that are rare or depleted on Earth. The ability to mine asteroids for resources could support space colonization efforts and contribute to the development of a space-based economy. However, this also presents challenges related to regulation, environmental impact, and the equitable distribution of resources. The development of a space-based economy will also require new regulatory frameworks. As humanity expands its presence in space, it will be essential to establish clear guidelines for the use and protection of space resources, the management of space debris, and the resolution of disputes between nations and private entities. International cooperation and collaboration will be critical in addressing these challenges and ensuring that space remains a domain for peaceful exploration and scientific advancement. As we continue to push the boundaries of space exploration, we must also consider the long-term sustainability of our activities. The management of space debris, the protection of planetary environments, and the ethical considerations of our actions will all play a role in shaping the future of space exploration. Ensuring that our activities do not negatively impact the space environment or other potential life forms will be crucial for maintaining the integrity and sustainability of our endeavors. The future of space exploration is a journey of discovery, innovation, and transformation. As we strive to become an interstellar civilization, we are not only expanding our physical boundaries but also exploring the limits of human potential and imagination. The quest to understand the universe and our place within it drives us to seek new frontiers and embrace new challenges. In this grand adventure, we are guided by our curiosity, our desire for knowledge, and our aspiration to reach beyond the stars. The journey is as much about exploring the cosmos as it is about exploring ourselves, our values, our capabilities, and our dreams. As we chart our course into the future, we carry with us the hopes and aspirations of generations past and the promise of a brighter, more expansive future for all of humanity. In the end, the exploration of space is not just a pursuit of scientific knowledge or technological advancement. It is a reflection of our deepest aspirations and our enduring quest to understand the mysteries of the universe. As we continue to explore and innovate, we are forging a path toward a future where the cosmos is not just a distant dream but a tangible reality, filled with possibilities that stretch the limits of our imagination and redefine what it means to be human. The journey ahead is one of boundless potential and extraordinary discovery, and it invites us to dream big, reach for the stars, and embrace the infinite possibilities that lie beyond the horizon. As we continue to contemplate the future of humanity in space, the implications of our ambitions and discoveries extend far beyond the immediate scientific and technological advancements. The evolution of our species into a spacefaring civilization will inevitably influence every aspect of our existence, from our social structures and cultural norms to our philosophical outlook and existential understanding. One of the most profound aspects of becoming an interstellar civilization is the potential to redefine our collective identity. As humans spread across the galaxy, each new settlement will develop its own unique culture and societal norms, influenced by its environment, technological advancements, and historical experiences. This diversification will lead to a rich tapestry of human experience and knowledge, reflecting the adaptability and resilience of our species. The emergence of new cultures in space will raise important questions about the nature of human unity and diversity. How will we maintain a sense of shared identity while embracing the unique characteristics of different spacefaring communities? The answer may lie in the establishment of common values and goals that transcend individual cultures, such as a commitment to exploration, cooperation, and the preservation of life. These shared principles could serve as a foundation for a universal human ethos, fostering collaboration and mutual respect across the galaxy. Moreover, the development of space colonies and interstellar travel will challenge traditional notions of governance and political organization. As humanity extends its reach beyond Earth, the need for new systems of governance will arise, addressing issues such as resource management. The creation of fair and effective governance structures will be essential for ensuring the stability and prosperity of spacefaring societies. One possible approach to governance in space is the establishment of international or interstellar institutions that can provide oversight and coordination across different settlements and missions. These institutions could facilitate cooperation, mediate disputes, and establish guidelines for the ethical use of space resources. The success of such institutions will depend on their ability to balance the interests of diverse communities while upholding principles of justice and equity. The exploration of space also brings into focus the philosophical and existential questions about our place in the universe. As we uncover new worlds and potentially encounter other forms of life, our understanding of ourselves and our purpose may be profoundly altered. The search for meaning in the vastness of space will prompt us to reflect on fundamental questions about existence, consciousness, and the nature of life itself. The possibility of encountering extraterrestrial civilizations would be a transformative event, challenging our assumptions about life and intelligence. It could lead to a reevaluation of our understanding of consciousness, morality, and the nature of sentience. The implications of such encounters would extend beyond scientific discovery, influencing philosophical, theological, and ethical discussions about our role in the cosmos. In addition to these profound questions, the exploration of space will have practical implications for our everyday lives. The technologies developed for space missions often find applications on Earth, leading to innovations in fields such as medicine, materials science, and environmental monitoring. For example, advancements in imaging technology used for space telescopes have contributed to improvements in medical diagnostics, while research on life support systems has led to innovations in water purification and waste management. The development of space infrastructure, such as space stations, lunar bases, and interstellar probes, will also have far-reaching impacts on our technological capabilities and economic systems. The creation of space-based industries, such as satellite communication, space tourism, and asteroid mining, will drive economic growth and open new markets. The commercialization of space will create opportunities for entrepreneurship and investment, fostering innovation and technological advancement. As humanity ventures further into space, the preservation of our home planet will remain a critical priority. The knowledge gained from space exploration can inform efforts to address pressing challenges on Earth, such as climate change, resource depletion, and environmental degradation. The insights gained from studying other planets and celestial bodies can provide valuable lessons for managing our own planet's ecosystems and ensuring the sustainability of our civilization. Furthermore, the perspective gained from space exploration can inspire a greater appreciation for the interconnectedness of all life on Earth. Viewing our planet from afar, as seen in iconic images such as the pale blue dot, can evoke a sense of unity and shared responsibility for protecting our home. This perspective can encourage a global mindset and foster a commitment to addressing global challenges collaboratively. The future of space exploration holds the promise of extraordinary discoveries and advancements that will shape the course of human history. As we strive to become an interstellar civilization, we are not only expanding our physical boundaries but also pushing the frontiers of human knowledge and imagination. The quest to explore the cosmos reflects our innate curiosity, creativity, and resilience, driving us to seek new horizons and embrace the unknown. In this grand adventure, we are guided by the spirit of exploration and the desire to understand our place in the universe. The challenges and opportunities of space exploration will test our ingenuity, collaboration, and determination. As we chart our course toward the stars, we carry with us the hopes and dreams of generations past and the promise of a brighter future for all of humanity. The journey ahead is one of boundless potential and limitless discovery. As we continue to explore and innovate, we are forging a path toward a future where the cosmos is not just a distant dream but a tangible reality. The possibilities that lie beyond our current knowledge invite us to dream big, reach for the stars, and embrace the infinite opportunities that await us in the vast expanse of space. As we look to the future, we are reminded of the enduring human spirit and our unwavering quest to explore the unknown. The exploration of space is a testament to our determination, creativity, and resilience, a reflection of our desire to understand the mysteries of the universe and our commitment to pushing the boundaries of human potential. In this grand adventure, we are not just exploring new worlds, but redefining the very essence of what it means to be human. The journey to the stars is a journey of discovery, growth, and transformation, and it invites us to embrace the limitless possibilities that lie ahead. As humanity stands on the precipice of interstellar exploration, our ambitions stretch further than ever before. The potential to become a multistellar civilization opens up not only new frontiers but also presents an array of challenges and opportunities that will shape the future of our species. This period of exploration and expansion will redefine our understanding of the universe, our place within it, and our approach to the myriad challenges that lie ahead. One of the most compelling aspects of this future is the potential to interact with and learn from diverse planetary environments. Each celestial body within our reach offers a unique set of conditions and characteristics that could provide valuable insights into the fundamental processes of the universe. From the icy moons of Jupiter and Saturn to the rocky surfaces of distant exoplanets, each new discovery has the potential to enhance our knowledge of planetary formation, climate dynamics, and the potential for life beyond Earth. The exploration of these environments will require sophisticated technologies and techniques. Robotic missions will play a crucial role in the initial stages, providing detailed data and analysis that can inform subsequent human missions. Advanced robotic systems equipped with high-resolution imaging, chemical analysis tools, and autonomous navigation capabilities will allow us to investigate the surface and subsurface of these distant worlds. These robots will serve as our eyes and ears, gathering essential information that will guide our efforts to explore and potentially inhabit these new frontiers. In parallel with robotic exploration, the development of human spaceflight capabilities will be essential for deeper exploration and settlement. Long-duration missions to distant destinations will test the limits of human endurance and resilience. Astronauts will need to adapt to the challenges of extended space travel, including the effects of prolonged exposure to microgravity, radiation, and isolation. Developing advanced life support systems, medical technologies, and psychological support mechanisms will be critical for ensuring the health and well-being of crews on these missions. The establishment of permanent settlements on other planets and moons will require the development of advanced infrastructure and technologies. Habitats will need to be designed to withstand the harsh conditions of space environments, including extreme temperatures, radiation, and limited resources. Innovations in materials science, environmental control, and energy generation will be key to creating livable and sustainable habitats. Techniques such as in situ resource utilization, where materials are extracted and processed from local sources, will be crucial for reducing the dependency on supplies from Earth and ensuring the long-term viability of these settlements. The social and cultural aspects of life in space will also evolve as we establish communities on other worlds. The development of new social norms, governance structures, and cultural practices will be shaped by the unique challenges and opportunities of space living. The experience of living in isolated and confined environments will foster new forms of social interaction and community building. The diversity of human experience across different space settlements will enrich our collective understanding of human nature and society. As humanity expands its presence in space, the ethical and philosophical implications of our actions will come into sharper focus. The potential for encountering extraterrestrial life raises important questions about our responsibility as explorers and the moral implications of our interactions with other forms of life. Ensuring that our activities do not harm or disrupt potential extraterrestrial ecosystems will be essential for maintaining the integrity of our exploration efforts. The development of a spacefaring civilization will also prompt us to rethink our approach to environmental stewardship and resource management. The lessons learned from managing space settlements and utilizing space resources will inform our efforts to address environmental challenges on Earth. The principles of sustainability and conservation that guide our activities in space will help us develop more effective strategies for managing our planet's resources and protecting its ecosystems. The integration of space exploration with other scientific disciplines will drive innovation and discovery across a wide range of fields. The study of planetary geology, astrobiology, and cosmology will deepen our understanding of the fundamental processes that govern the universe. Advances in space technology will have far-reaching implications for industries such as telecommunications, transportation, and medicine. The cross-disciplinary nature of space research will foster collaboration and creativity, leading to new breakthroughs and advancements. As we look to the future, the potential for space commercialization and entrepreneurship will continue to grow. The development of new markets and industries in space will create opportunities for innovation and investment. Space tourism, asteroid mining, and space-based manufacturing are just a few examples of the potential applications of space technology. The commercialization of space will drive economic growth and create new avenues for human exploration and discovery. The pursuit of interstellar travel represents one of the most ambitious and challenging goals of our time. The development of technologies capable of reaching other star systems will require significant advances in propulsion, energy generation, and spaceflight systems. Concepts such as the warp drive, which theoretically allows for faster-than-light travel, and the concept of generation ships, which support human life over long durations, will be explored as we seek to overcome the limitations of current space travel capabilities. The quest for knowledge and exploration will also be guided by our curiosity and desire to understand the fundamental nature of the universe. The search for extraterrestrial intelligence, the study of dark matter and dark energy, and the exploration of cosmic phenomena such as black holes and neutron stars will continue to drive our scientific endeavors. Each discovery will contribute to our understanding of the universe and our place within it, expanding the boundaries of human knowledge and imagination. As we venture into the cosmos, the importance of international collaboration and cooperation will become increasingly evident. The challenges of space exploration are too great for any single nation or organization to tackle alone. Collaborative efforts between countries, space agencies, and private entities will be essential for achieving the goals of space exploration and ensuring the peaceful use of space resources. The spirit of cooperation that defines our space endeavors will help to build bridges between nations and foster a shared vision for the future of humanity in space. In this grand adventure, we are guided by the spirit of discovery and the desire to explore the unknown. The journey to the stars represents the culmination of human ingenuity, ambition, and perseverance. As we chart our course toward the future, we carry with us the legacy of those who came before us and the promise of a brighter, more expansive future for all of humanity. The exploration of space is not just about reaching new worlds or uncovering new knowledge. It is about pushing the boundaries of human potential and embracing the infinite possibilities that lie beyond our current understanding. The quest to explore the cosmos challenges us to think big, dream boldly, and reach for the stars. It invites us to embrace the unknown, to learn from our experiences, and to continue striving for greatness as we venture into the vast and wondrous expanse of space. In this ongoing journey, we are not only expanding our physical horizons but also deepening our understanding of ourselves and our place in the universe. The exploration of space is a testament to the boundless curiosity and resilience of the human spirit, and it offers a glimpse into a future filled with endless opportunities and possibilities. As we continue to explore, innovate, and discover, we are forging a path toward a future where the cosmos is not just a distant dream but a vibrant and integral part of our collective experience. The journey ahead is one of transformation and discovery, and it invites us to embrace the limitless potential of the universe and to envision a future where humanity reaches new heights and explores new frontiers beyond our wildest imaginations. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video if you found this video helpful and subscribe to the channel for more such amazing videos.